Now that we've reviewed the idea of a limit, I wanted to present some properties of limits, and then after we've looked at these, go through a few examples of how we can actually find limits using these. So in these numbered properties here, we're going to assume that c is some constant. So the first property simply says the limit as x approaches a of a constant is just the value of that constant. The second property says that the limit as x approaches a of x is a. So we could simply think of the line y equals x and consider traveling along that from either direction and see that as the x value approaches a, it makes sense that the y value would as well. Property 3 is essentially thinking about constant multiples. What we're saying is that if I have c times f of x, and I'm taking the limit as x approaches a, I'm allowed to take constant multiples and bring them outside of the limit. So for property 4 here, looking at the limit of a sum of two functions, what we're saying here is that I can express that as a sum of the requisite limits. Number 5 says the same thing for subtraction, 6 for multiplication, and 7 for division, with the caveat that we don't want to divide by 0. And finally, for these last 4 properties, 4, 5, 6, and 7, it's important to note that this is making an assumption. So I'm assuming that the limit of f of x as x approaches a and of g of x as x approaches a, that these limits exist in order for me to make use of these properties. So what does this look like in practice? Let's consider evaluating some of these limits. So for this first one here, I want to find the limit as x approaches 5 of this function, x cubed minus x over 2x plus 3. So I can break this down, and I don't necessarily need to write out all of these steps. Of course, it would be fine if I did. One thing I'm thinking about is that I can find the limit of the numerator and find the limit of the denominator and use what I referred to as property 7 here. So I can kind of focus on those separately. Of course, assuming those exist and the denominator doesn't approach 0, which we see is true here. And then within there, I have a few things. We know that the limit of x, in this case, just that part alone should be 5. I can likewise think about the subtraction rule in there to kind of focus on the numerator separately, and think of the product property that we saw above to express this as 5 cubed. In the bottom, we can use the addition rule to know that we know the limit of 3 is 3, the constant. And 2x here, I can now go back to property 2, where I know what the limit of x is, and property 3, here my c value is 2. So these are all things that I could break up into a bunch of steps. But again, with this being preparation for Calc 2 with a recap of limits, the idea is that you don't have to write down all of those steps, but we are making use of those properties. So in particular, what's happening in this instance, and what we can in some sense try when we approach limits, is I can actually just substitute in the desired x value of 5. Now, we're going to see that that doesn't always give us something meaningful, and we have different ways of finding the technique. And the other thing we're going to see here is that being able to do this has a connection to continuity, which I'll cover in the next video. So this is the approach I'm going to be able to use to evaluate this, and so we can simplify this fraction. Now in the next example, the idea of plugging in infinity in the way that I plugged in 5 doesn't really make sense here. So what we can do in this instance is try to simplify this. The thing that is making this difficult is both the top and the bottom are approaching infinity, and this notion of infinity divided by infinity is not something that is easily understood. So what we can do instead is manipulate the function that we're taking the limit of. So one thing here is I'm noticing that the infinity is kind of dominated in some sense with these x squared terms. One thing I can do that won't affect my limit is I can divide both the numerator and the denominator by the same thing, that is, divide it by x squared, and think about what happens there. So if I divide everything in the numerator by x squared, I'm left with this. And if I divide everything in the denominator by x squared, I'm left with this. Now, this is a little bit easier for me to think of because we've already talked in an earlier example in a previous video about 1 over x squared. That as x goes to infinity, that's going to approach 0. You can think of that, the denominator is growing without bound, top's constant, that fraction is going to approach 0. So as I send x to infinity, that part will vanish. And that will be true for these other pieces that have a constant divided by a power of x. So I'm left with the value 3 in the numerator and 2 in the denominator. And so that's going to be our final answer. So number 3 here, in some sense, this looks a little bit like number 1 in terms of what we're trying to find. So I might approach it like we ended up doing in 1, and I try to plug in x equals 1. But that's not going to work here. So when we plug in x equals 1, notice that the numerator evaluates to 0, and so does the denominator. And what is 0 divided by 0? That's not going to lead us anywhere. So while it was fine to try it, we have to kind of come back and reconsider this. Well, what I can note is that it's significant that both the top and the bottom evaluate to 0 at 1. 1 is actually a root in this case. So notice that the top, I can take advantage of that by factoring. So if I have x minus 1 and x minus 4 multiplied together, that's what I get here. The reason this is useful is that in terms of finding this limit, we can cancel the common factor from the numerator and the denominator. And importantly, this is, again, where limit is important, that it's not saying what's happening exactly at this value. So this isn't defined at 1, but we can find the limit as we approach 1 here. And essentially what we're saying is, well, what's the limit as x approaches 1 of x minus 4? Well, that's going to be 1 minus 4. It's going to be negative 3. Now, this next one, again, dealing with infinity here, while this might look a little bit like number 2, it actually has a key difference. So let's think about what we're taking the limit of here, x squared, and then I'm going to rewrite 3 times x to the minus 1 is just 3 over x. So it's not the same in the sense that we don't have infinity in the numerator and infinity in the denominator. Instead, as x approaches infinity, this 3 over x is going to go to 0. So the denominator is approaching 2. The numerator is approaching infinity, so we're thinking about this expression where the numerator is going to grow without bound. The denominator is going to approach a finite number. In this instance, the limit's just going to be infinity. You have something approaching infinity and we're dividing it by something approaching 2, we're still going to think of that as infinite. So we have to be careful about how we approach things once we start to have infinity involved, and that's also going to motivate another technique we're going to deal with in limits in class. And then finally, my last example here, again, trying to plug in the limiting value of negative 4, we're going to get 0 over 0. So kind of like number 3, when I see something of this nature, my goal is to try to rewrite the expression in some way in the hopes that that can help me solve the limit. So let's think about doing that. In particular, when I look at the numerator here, I'd like to combine those functions. So if I want to do that, I can get x plus 4 over 4x. And all of a sudden, notice what's happening here. I have in the numerator here, I have an x plus 4. Let's use a different color. And I have an x plus 4 down here. So what happens is now it's equivalent to us asking the question, what's the limit as x approaches minus 4 of 1 over 4x? And that's going to be negative 1 over 16, plugging in negative 4 for that value.